Okay, so thank you again, Oles, for the wonderful session on automation. We're going to talk a little bit about, we're going to shift the focus to how we generate some of this data from first principles calculation. Okay, so, and that's going to be the focus of the workshop today, is how a lot of this data is going to be generated, how we use AI in generating it, how we leverage AI after we've generated to learn more about the data. These are the topics that we're going to be covering today. And we're going to focus particularly on thermodynamic modeling. From that perspective, the main question that I want to focus on today is whether a material is going to form or not. Okay, so we can think about taking various components, and the question is, if we take a mixture of components, maybe components we've never tried to mix before in the lab, will it form, what is it going to form into, what structure, and how do we determine that, how do we predict that, okay? So talk today, I'm going to acknowledge a number of collaborators from the AFLOW Consortium. Of course, our people have helped sponsor the event today. So I'm just going to start off with the discussion of what does materials discovery mean, and the materials development from the perspective of this talk, okay? So I know I've seen a lot of you in the audience that have seen some of my lectures in material science. For those of you that are outside, what does it mean to develop a new material? Why is it so important? So we start off with materials that are naturally occurring, that we can find in the ground, okay? Something like iron, copper, bronze. These are the materials that have helped define the age and the technology that we're using, right? A lot of people would characterize today as a silicon era, okay? These are computers. So we can take these materials, we can characterize them for their properties. Okay, so maybe they're magnetic, they conduct electricity. We can basically run them, run an experiment to characterize the material for its properties, and then very linearly we can just map that to an application space. Okay, so if it's magnetic, conducts electricity, maybe it's good for electric motors, electronic circuits, what have you. It's a very linear approach. Okay, I like movies, and so I like to use the notation here, Deus ex machina. If you're familiar with the term, it's as if we're waiting for the solution to fall from the heavens. Okay, it's a very passive approach. We want to work the other way. We want to start with the application in mind and think about what are the set of properties that we need to optimize in order to have the best material for that application. Okay, so think about catalytic converters here. We talked a little bit about catalysis this morning. We want something that has good catalytic activity, something that has high temperature functionality, chemical attack resistance. You can name the set of properties, and now it becomes an optimization problem. Within that realm, how do we find the materials that within those constraints would be the best serving material for that application space? This is an active approach. Okay, so this is what we mean by materials discovery. Using first principles calculations. A lot of people think that because we do calculations like Oli showed earlier, the computational person at the desk, we don't actually make any real new materials. But I can tell you that these methods are incredibly powerful. And we have been able to make new materials from prediction first and then validating them experimentally. Okay? So this is flipping on its head the typical workflow of material science. Okay, now I'm just going to give you a quick set of examples. We've helped discover 2 new rare earth-free magnets. These are the first magnets discovered by computers. Okay, and they're very important because rare earth, despite the name, are not exactly rare, but they're difficult to mine. Where we mine them can be, they come from particular places on the map. And so the geopolitics plays a big role in the cost of these materials. And so generally speaking, we want to move away from them. And so we helped discover 2 new rare earth-free magnets. I'll talk about these studies in more detail throughout and how we use first principles to discover them. We helped discover 2 new cobalt-based superalloys. 2017, we had a paper, we published a number of predictions, and then an experimental group independently verified 2 of them in 2018. So you can see how there's different ways that you can find new materials. One way where you do the whole loop of finding the material, validating the prediction, and then you can even offer predictions to the community, have them validate. We've discovered a number of new high entropy systems. Actually, this is not going to be a topic we talk about today. This is another lecture that maybe we can do for another time. But these materials are going to, for sure, play a big role in high temperature structural materials. Okay, so we've discovered new carbides, borides, carbonitrides. We've had a number of papers in this area, and it's a very fruitful area for computation. Lastly, one that I'm very interested in talking about and I hope I get to with the time, is that we help discover new phase change memory composition. So everyone understands that CPU performance doubles every year because every year we can double the number of transistors on the integrated circuit. That's Moore's law. What's not often talked about is the lag in memory performance. So we can do a lot of calculations, but can we store the data, the subsequent data? That's a big challenge. And why I think this is really important for today is because this was part of a closed loop, multi-institution effort with a closed loop AI that was looking for these types of materials. Lost the leader. So we're going to talk a lot about AFLOW. AFLOW is a tool that is open source. Well, there's two parts to it. It's a tool, it's a C++ based code, it's open source. It's also a database. It's all under one name. It's one of the largest databases for inorganic materials. You can go on AFLOW.org and see that, and there's a lot of studies that base their predictions, the new materials on data that's been calculated in AFLOW. We're going to talk about why it's important to use a tool like AFLOW when you're performing your first principles calculation. So first and foremost, the name of the game really comes down to standardization. Someone here on the right side of the room wants to run a DFT code, perform an analysis. They may not come to the same conclusion about parameter sets, grid sizes, convergence criteria as someone on the left side of the room. And that makes it very challenging for machine learning models to be able to learn from this data because they might be picking up trends just from the variance in the parameter space. So I'm going to talk a lot about standardization of these calculations and why it's so important. But first and foremost, we have a density of states plot here for some of the material science students here. What do we have here? Metal, semiconductor, insulator?
Metal.
We have a metal.
Wait, oh, I thought you were...
What do we have? That's the guess?
You're asking what we do.
Up there? Okay. Any other guesses? We have only one more choice, insulator. I'll say this. Okay, so we have it's a semiconductor, but effectively, if we know this is a very nice semiconductor. The gap is small enough that we can dope it, and that's by definition a semiconductor. So we have this gap here. Okay, this is probably the first materials property you may have ever learned from your class. Do we have a metal or an insulator? Okay, but the key piece here is that a lot of people don't know that this actually comes from a much bigger plot called the electronic structure. Okay, and so what we need to do to analyze whether we have an insulator or metal is really study this big structure here. This is something that we can get from density functional theory that we can calculate. Okay, basically what this map tells me is where and how the electrons can exist energetically. Okay, so the fact that there's a gap here means the electrons cannot exist there, and that's what gives me these very nice semiconducting properties. So this space that this x-axis here is really a walk in the reciprocal space. Okay, we're not going to get into too many details of the physics here, but effectively to understand the electrons in a periodic system, we need to map it to, you can think of it like the frequency space versus the time space. We're looking at this from a spatial perspective. So we can look at our crystal lattice in this reciprocal space, which is a mapping for the fact that it's a periodic. And we need to do a walk in this crystal to sample all the unique spots and see how the electron states exist. Basically, we're solving Schrodinger's equation along a 2D walk in this space, okay? How we perform this walk and making sure that we perform the smallest walk, or the least longest walk, has been it was a challenge, and it's been standardized. This is actually one of the main features that put AFLOW on the map, was that these walks for all of the different types of crystals have been standardized and codified into AFLOW. And so this is one of the standardizations that AFLOW's tackled early on. Another type of standardization really comes from how we leverage one type of density functional theory called VASP. We'll talk a little bit more about that in the workshop. But we've basically established a number of criteria that make the calculation useful and reproducible. Okay, so from that perspective, we need to define what are these convergence criteria, what are these different parameter sets, the different grid settings. It's not just a matter of we have a 5 by 5 by 5 grid, because depending on the chemistry and the structure, we need to change these grids. So these parameters are not just constants, but they need to adapt with the different chemistries and with the different structures. And so we discussed these heuristic rules that have come from many years of running these calculations and how we define those thresholds. So this is the main idea, that by having this standardization, it really enables machine learning. It makes a very nice environment for learning, because these trends, even though we know, for example, that DFT has some shortcomings, we can hope that these shortcomings eventually become systematic errors that the machine learning algorithm will not pick up, and it'll actually be able to tell us useful chemical trends across a broad space of structures and chemistries. Another standardization type that's even more challenging, that's being tackled for a number of years, is structure standardization. So I'll walk you through that. Here we have a half-Heusler structure. This is a well-known structure. It was discovered during World War II, silver, arsenic, and magnesium. And this is how we found the material containing this and having this structure, this backbone. What we can do is we can extract out the chemical agnostic backbone. So where are the generic sites where the atoms can sit? And then you can think about redecorating that structure with different components. Okay, this is actually one way that we make new materials. And so we can redecorate it with a number of different combinations from the periodic table and get a number of different properties. Okay, so we can do this on the computer. We don't even need to worry about the fact, does it exist? So that's the main question of the session today. But fundamentally, we can calculate its properties. So it's not just as simple as having someone sit and go through all the literature and picking out all the unique structures, because a lot of these structures have been reported in different ways. If you took a material science class, you would know that there's no unique a representation of a crystal. You have many different representations of the crystal, and there can even be non-unique primitive forms of the crystal. So how this crystal is represented is not always obvious, and there's some settings that are obsolete. It's a big challenge. Okay, so it's really understanding what the symmetry of the structure is, what the Wyckoff positions are. So this is a big effort that's been going on since about 2017, and there have been a number of volumes that have been published. There's over 1,000 prototypes, probably approaching 1,500 at this point. But so now you can imagine we can take these backbone structures, we can redecorate them with combinations of different elements from the periodic table. Okay? But this becomes a combinatorial nightmare. There's more combinations here than there are atoms in the galaxy. Okay, so we still need to figure out a way to screen this much faster. And so if you read papers in the field, you're often going to see this funnel, because we usually start with some subspace of materials, some class of chemistries and structures of subspace, and then we try to figure out how we can funnel through the most interesting candidates. Okay? One of the arguments that we try to make is that one of these rungs has to be stability. Okay, a lot of times we can just look at the properties, but we don't necessarily understand stability. Stability is not a single thing, because you could have a device that operates at different temperatures, different pressures. We need to understand stability under those operating conditions. So we can look at thermodynamic stability, mechanical stability. We can look at application-specific criteria. So we can have something like the superconducting critical temperature of superconductors. We were looking for room temperature, right? That's the big search. We can look at the Curie temperature for magnets. Okay, at what point does the magnetization turn off, temperature-wise? And then for superalloys, we can look at mechanical properties, so two-phase equilibrium, we'll talk more about that. Thermoelectrics, we can look at the ZT, right? So we want to optimize the ability for it to convert, to generate electricity from heat. Okay, so we're going to cover two main informatics tools. First is the ability to create a first principles-based phase diagram. So can we fundamentally understand the stability of these materials? The main question is it going to form a single phase, or is it going to decompose like oil and vinegar? And then on the other side here is descriptive generation. So at some level we're modeling these materials, and we understand that we're working with atoms, we can shift them around on the computer, but these correlate to macroscopic properties. So we want to figure out, are there functional relationships between the properties that we can calculate at the nanoscale that translate up to the macro scale. Think like hardness, right? For example, hardness is a good example, because you can have hardness really scales many different length scales. So you can think about hardness from the bonding of the atoms, okay, so the bonds between them, but hardness is also affected by microstructure. And so there's a lot of different contributions to hardness. We need to consider all of these things. So at some level, we want to understand the structure-property relationships. Here we have a very famous high-temperature superconductor. What about the structure here? What about the chemistry? What are the pieces that give us this phenomenon? And more than that, we know that there exists, just to stay in the example of superconductivity, there are many different types of superconductors, all of them having different structures, different chemistries. What is the similarity between these sets that give us the same phenomenon? Okay, those are the questions we hope to answer. So I'm going to cover this quickly because we're going to go through it in the workshop, but I'm going to set it up as an example for how we found new materials. Here we have a plot of the energy versus composition. We're spanning alloys of palladium and platinum. And so you can see here at the 50-50 concentration, we have one type of structure that's half palladium, half platinum, and then we can have a different atomic arrangement. Think FCC, BCC, those different types of arrangements. And then we can also span the different compositions, ratio of blue to white. Okay? And so our goal is to understand what are the set of points on this graph that are not going to decompose into any other linear combination. Okay, and this is called the Convex Hall. We're going to show you how to calculate that and a little bit about the algorithm. But effectively, you can just think about wrapping a giant rubber band around. Okay, the points that it touches are the stable points. And really, the bridge here is that if we try to mix these two components in the lab, well, let's do the 50-50, we expect that it's going to form this system. And that's what the calculations are telling us. And then we need to see, do those calculations match experiment? So here we have a facet which shows us that we have two-phase equilibrium. Basically, it says that if we try to mix something in the middle here, it's going to phase separate into these two components here. Okay, they happily coexist like oil and vinegar. We use that concept to find new superalloys. So one of the very important mechanisms for making a material very hard is called age hardening. And through a series of quenching and annealing, basically temperature treatments, we can go from something that has basically this structure, this host matrix, where it's basically aluminum, and we have some dopants of copper. We can go from that to a new type of structure where we form these precipitates. You can think of them as little nuggets inside of the material. And what they do is, this is really another phase inside, and what it does is it prevents the dislocation of the movement it prevents the movement of dislocations and it makes it harder. And so what we want to understand from a computational perspective, and we map this to our phase diagram here, is that let's imagine that we have a set of compositions here, the red line, that we know could be this precipitate composition. Okay, that's the range of compositions that this precipitate could be. We want to understand, is it possible that we can form this blue line here, mapping the host matrix, basically pure aluminum, to the set of compositions that the precipitate could take form in? And so you can imagine that if I have a facet line that looks like the green one here, as I scan all the different ternary combinations, if this facet line exists, this blue line will not exist. I can't form that blue line. On the other hand, if the phase diagram has a facet that looks like the black line here, then there do exist a range of compositions here, a narrow one, where you can have that tie line exist. Okay? And so by scanning all these different ternary phase diagrams for a descriptor that has this mapping, we're able to come up with a set of predictions of most likely candidates for new superalloys. And then in 2018, as I said, there was a group that independently picked this up and was able to show this nice gamma prime structure in these structures, which is canonical for the superalloys. Let's go back to this picture. So we have obviously not all of the points to find the hull here. All of the points that are off the hull are unstable. Okay, so effectively, if I try to make this composition, it's going to decompose into this linear set. You just drop your line directly down and look at what the facet is below it. So we can define this decomposition reaction. Okay, if I try to make that composition, I expect it's going to phase separate into this reaction. And I can even quantify the energy of that reaction. Very simply, it's just the distance on this picture. Okay? This was an understanding that Gibbs had, and you could do these calculations very simply just from that distance on the y-axis. So we get 3 MeV per atom. Is that big? Is that small? We have a threshold here that we generally define. We can compare it to room temperature excitation. Okay? And so that's about 25 MeV. So we can say that this structure may form at room temperature. Okay, you can think of the 25 MeV as like an error bar that tells us that at room temperature, what is it likely to form, even if it's not the most stable, because these calculations are performed at 0 temperature. Okay? We took this concept, we flipped it on its head, because there are often times when we do materials discovery where we get a lot of stable structures. Now we need to sort through and figure out what are the most stable structures that are most likely going to form. So how do we differentiate between those that are predicted to be stable? So what we did is we defined this criteria very similar to here to the decomposition energy. We took, if we're interested in understanding how stable is this point here on the hull, we take this point, we remove it, we recalculate the hull without it. You see how the shape changes. Okay? And then we calculate the y distance here between the point and the new hull. And so you can imagine this is very well populated. Okay, so we have a lot of calculations here. But in some sense you understand that there may be new phases that we've never thought of calculating. Okay, so in some sense, what is the probability that if I find some new phase in the laboratory, then took that and calculated its properties, that it's something down here which completely changes the hull, and now this point isn't stable anymore. So if this distance is very large, that probability is very small. So the larger that distance is, the bigger the impact that point has on the convex hull. Okay, so we want to filter out for points that have very large stability criteria. That's what we call it here. This is 6 MeV, it's not very large. Okay? We use this criteria to find new magnets. Okay, so here we have the Heusler prototype. There's 3 different types of structures. Okay, the regular, the inverse, and the half Heusler, the one I talked about earlier. We can take this prototype, redecorate it with 51 different components. All of these components at some point have been seen in the Heusler structure. We can form new compositions. We get something like 2,000 different candidates. A lot of these were stable, a lot of them were magnetic, so we needed an additional criteria for filtering out the most stable structures. And we used this stability criteria. We basically said, is that distance greater than 30 MeV, right? That's bigger than that 25 MeV threshold that I defined earlier. So that's a really big gap. And so we used that criteria, and we looked at which ones were stable to it or not. That distance was larger, and we found we actually had 4 candidates. We tried them experimentally, and 2 formed. Okay, it's 50%. It's not a very good amount in a test, but that's super for materials discovery. And we went down from something that had possibly hundreds of thousands of possibilities down to 4. That's a manageable amount of experiments to try. And you can see the results here, smaller. We can see that it's magnetized. And this plot here tells us that it's also the Heusler structure we predicted. So in a lot of ways, these predictions were validated in many different respects. So you can do this. I've been showing a lot of 2D plots. You can do this in 3 dimensions. You can actually do it for arbitrary number of dimensions. It's just, we can't plot it. I can't show you what a 4D one looks like, 5D, but you can go up to, you can increase the number of components, which critically becomes very important for high entropy systems, for example. But so we can do this analysis, and you can even do it on your computer. You're going to do that today in the workshop. So you can run this from your laptop, because what happens is, so we've set up an API system where you can grab the values of the energies from our database. From the database, this is going to be pulling data from the AFLOW database, and it can actually perform the analysis on your computer. Okay? And so as new calculations are added every day, you can refresh it and get the most up-to-date analysis of what that convex hull is going to look like, what are the stable points, what is the stability criteria. We have, you can get the data in a nice report form. You're going to see that later. You can also get it, more importantly, in JSON form, which is very nice for integrating with Python, and therefore using scikit-learn, machine learning, etc. Okay? So one of the challenges I want to pose for all of you is, it's very difficult. You can imagine, hey, these calculations are very expensive, because I have to do a DFT calculation for every one of these points, and there's a lot of points that are not even going to be on the hull, and we're going to do those calculations anyway to see if it's on the hull. So it's a big effort computationally. Question should be, can we do this with machine learning? Can I predict the energies of these materials from machine learning? How many of you think yes? Raise your hands. Can we do it with machine learning? How many know? Okay, good. Okay, so the answer is that it obviously depends on the accuracy. The accuracy of the best convolutional neural net is about, I think it was about 30 MeV per atom. Okay? So within that range, you can say, okay, we're doing pretty well calculating the energies. But the problem with this construction is, let me go back to show you the picture. Imagine a 30 MeV error bar for every single point here. We have no convex hull. So while we might be able to say that we can predict the energies to within 30 MeV, we need something much smaller for doing the thermodynamic analysis. So that's very important to keep in mind, because we need the energies of all of these to be consistently right. More right than maybe the threshold we would define normally for the energies, because it's a construction of all of these energies combined. So if we had big error bars here of 30 MeV, we would have no reliability of this structure. So thermodynamics is a more difficult criterion to predict, and at the moment we cannot do it with machine learning. If we could, then we can get rid of DFT, and we can run everything with Oses' models. So I'm going to show work here that actually is the first work that I did with Oses. I was very excited to be part of this work. So what we have here is a mapping of material space, okay, a 2D mapping. So what Oses did here basically is he created a network of materials. So some of you may have seen this for Facebook, where you have you might be a data point, and you can see all your friends around you, and then you form a cluster, and then there might be another friend which is connected to another big cluster. You can analyze the network for how many of these bridges exist. Okay, so basically he formed a network of materials here. This is what material space looks like. Okay, don't worry about how it's calculated. I'll tell you about that in a minute, but take this for granted that this is what the material space looks like, where if you're very close, there's a level of similarity between the materials. And the similarity here is defined with respect to the band structure concept I talked about earlier. How am I doing on time? Okay, I'll take another few minutes on this. So, what we ran is we looked at we tried to see if there are any trends in the clusters. And so you can see here that generally speaking, we have metals at the top, insulators at the bottom. So there's nice separation between these two different structures, right? And then on the right and left-hand wings here, we have small band gaps, semiconductors, and then ceramics here, metal, non-metal combinations. So you can see how different classes of materials have separated, okay? And generally speaking, within these realms, we find very similar types of materials. And what Oses did was very interesting. He took the superconducting critical temperature, and he mapped it on the same plot, okay? And what he found was that there's this band of high temperature superconductors here, okay? Now what's really interesting and troublesome about this is that we know for sure that density functional theory cannot calculate superconducting critical temperatures, because this is a highly correlated phenomena, and DFT doesn't get that at all. So how is it possible that it's able to find this region of high temperature superconductors if it can't even calculate the superconducting critical temperatures? So this is one of the big features I think that's really important for machine learning, is that, so if you look at the chemistries of these, a lot of them are oxides, first and foremost. So if they're all oxides, you can imagine that they might have similar band structures, at least similar features in the band structure. And that's what it's telling me here. But more so, what we need to take away from this is, perhaps we cannot access the property of interest, but certainly materials don't live in isolation. There are other ways that materials are similar. So maybe they're not similar through the maybe we can't calculate the superconducting critical temperature, but they're going to be similar in other ways that we can quantify with DFT. And so we have a back door to these properties that are really difficult to get to. And so the electronic structure for sure is going to play a role in superconductivity, but for example, we need the phonon analysis, we want to know how vibrations work, and then additionally, the electron-phonon coupling. It's critical for understanding superconductivity. So you can imagine as we add more and more and more data, this band here is going to shrink, okay, of similar properties. And so you can use this again as a map to say, if I find a superconductor here, I want to look at its neighbors for new types of superconductors. That's how you would use these maps. For those of you that are familiar, MgB2 is a very interesting superconductor. It's without going into too many details, it's got a very high temperature, but it realizes this through low temperature mechanisms. Okay, so it's a very interesting one, and this analysis showed that it was orphaned. So it's not similar to any other one, okay? I'm gonna wrap up with just the analysis here so we can get to lunch, but I wanna show you how this is built. So what you can do here is you can imagine taking the band structure construction that I showed you earlier, and we're gonna look at all of those points where we take turns in the Brillouin zone, okay? They're called high symmetry points. Okay, basically where we have all of these turns in the Brillouin zone where we do a 2D walk, and we can discretize and count the number of bands that go through all these bins, okay? So you can see here that one band crosses here, so that's gonna be a 1. This is 0, this is 0, this might be 5, I don't know how many are running through here, but you can see how I'm building a vector. A vector. And so we can build a piece of this vector and then we can concatenate them together to form this feature vector, okay? Fundamentally, this is the challenge of materials informatics. How do I define that vector? Okay, so we can take this vector is now a fingerprint of the material, it defines the material uniquely, and we can do an analysis of similarity between vectors, so we can define this space, we can figure out how they're different based on this vector, okay? Now I'm going to talk about how we get this. This to me looks like Texas, okay? So we, when we were working on the paper, we got some heavy criticism from some of the other co-authors because they said, what the heck are the axes on this plot? Do you remember? Yeah. So we had some angry co-authors that said, what are the axes on this? It doesn't make sense. So this doesn't have an XY axis per se that are meaningful, okay? The real meaning of this plot is the distance between points, whether they're similar or not similar, okay? And so the idea here is that in order to get this plot, we put these points all randomly in space, and then we perform a series of quenching and annealings, where all the points are going to experience a repulsion, a Coulomb repulsion. So they all want to separate. And then if they're similar to within the criteria we define within the band structure, how we define it, if they're similar, they also experience a harmonic attraction. Okay? And so you can see how we quench, and then some of them are going to cluster because they're similar, and then the ones that are not are going to form clusters elsewhere. Okay, so we perform these clusters all over and over and over again until we see something like this. Now we might get Texas rotated, if you were to run it on your computer, for example, but fundamentally Texas is what we would expect to get for this construction. Okay, I'm gonna just wrap up with some ideas on the fingerprint vector. This is gonna be the last slide. So, some key points on how we define this, because in my opinion, this is the most important and most challenging aspect of machine learning. How do I define this vector? Okay, generally speaking, for materials, for sure, it's going to contain information about the chemistry. So if we have a material that contains carbon, we take all the properties we know about carbon. What's its melting temperature? What is its space group? What is all of these, the element number, the period, all these different pieces of information. You can imagine forming one number after another for all of these critical properties of carbon. And if we had nitrogen, we concatenate to it, right? So you can imagine building a vector that way. So it's going to have properties of the elements concatenated. One of the key features to keep in mind is that there are a lot of models that are dependent on just that information, just the compositional information. We're hoping to get something which also includes the structural information. Okay? Why is that important? Because if we don't incorporate the structural information, then graphite and diamond are going to give you the same results. And we know these are two completely different materials. So we need to look out for how we incorporate structure. Okay, so most models are compositional, and you need to be careful about that. How do we include the structural information? There's a lot of different approaches that people have tried. Bag of bonds. We're not going to go into details, but you're going to see these words in the literature. Radial distribution function. You can imagine just an averaging of the distances of atoms as you go away from these atomic centers. Voronoi tessellation and fragments is an approach that I worked with on Oles, and I have the citation here if you're interested. And then the big one here that Oles was talking about today was convolutional neural nets. That's going to be able to incorporate the structural features. The problem is we can incorporate more and more and more features. These become really big, tremendously big. So it's more important to figure out what information do I not include in my feature vector. So the question here is about feature engineering. And you can imagine taking sets of these and forming new arrangements. So for example, maybe the property is not dependent on the melting temperature, but it's the melting temperature times the group number, or times the period. So you can form combinations of features. Now this is into the billions, trillions. You can think of this is growing exponential factorially. So there are approaches, automated ones like CISO. I'm not going to talk about it now, but CISO is a nice way of screening through these different combinations and figure out which ones are going to be the most relevant. And then I'm just going to end on this, that this is a heuristic. Of course, this is not necessarily true, but this design of the fingerprint really matters more than the algorithm. Okay? A lot of senses, the algorithms are important because some of them can take data in different structures. The algorithms are going to be important because some of them achieve higher accuracies just by construction of the algorithm. But fundamentally, at least from a material science perspective, if you figure out how to incorporate the necessary physics in your feature vector, more or less the different algorithms should work. Okay? And so with that, I can take questions as we start to do lunch, but I'm already over time. So I appreciate your time and your attention. Thank you very much.